Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be going adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Thank you.
These are early days of you in our college. Hope your stays are very cozy. Any problem you are facing? Okay, you should tell me. I've already shared with my phone number, email ID. You can drop it. Mm, I hope the things will be very wonderful because we are not dealing with a very wonderful subject called physics. Okay, we'll be thinking physics will be uh, me so that we can interact in a much better way. So this is in this third class. Okay, this is third class in a row of our quantum mechanics one course under your physics one, that is ph 101. As you can see, I told you I have clarified the basic, that is what is the necessity of this physics one course in your engineering program. Okay, and we started our journey with the most modern topic, that is called quantum mechanics 1. It's why quantum mechanics 1 has been chosen as the first topic, because this is a building block of many things you'll be learning in your semiconductors, uh, in your all in the cases of say lasers, what happens there, in case of the latest computation that is waiting for you, that recently Google has come up with quantum computer. We literally explored that, and all these things need some profound knowledge of quantum mechanics. Okay, I've told you last day also, today also I'll remind you. We'll learn quantum mechanics in two steps. We'll be talking about quantum mechanics one in first year, where I'll be talking mainly about theory, that was carried out between 1900 to 1927. And in second year, we'll actually apply all these ideas. So first year studies are very important because this is going to build the theory. And second, they are all applications in majority of the physical situation that you are now dealing with. You're now trying to just get the names, diodes. What is the phenomena taking place? Okay, you have to explain that quantum mechanically. So electron moves in a metal easily, but in an insulator, electron motion is restricted. Okay, they are bad conductors. Why? You have to explain that quantum mechanically. So quantum mechanics will be there to help you. And the latest materials called, all that, our life is now that everything is becoming small and small and small. That is the advent of nanotechnology. So these are all nanotechnologies learned in the language of quantum mechanics. So that's why you have chosen that as our topic. Okay. So the objective of today's class is that last day I told you that we'll be it all started in 1900, and in first year courses we'll be mainly learning about the more theoretical, a lot of experiments in details, and at the end of the experiments we are supposed to develop some new concepts which will be actually applied in our engineering program. Okay, so that is what you are trying to do. Okay, So I started with the experiment of black body radiation that was explained by Max Planck. So what I did, I have been very fundamental. I have tried to tell you what is called a black body. Okay. I first started with basic definition of radiation, what is called a black body, then experiment with black body radiation. Okay. So just let us quickly revisit whatever I discussed in the last lecture. Okay. This is a third class in a row. These are all my contacts, as you can see there. This is me. Okay. And you can see there. Any problem you face, you contact me, phone me. These are the course objectives and outcomes I illustrated last day, and I told you the most important person, now is Mr. Planck. Okay, the Planck constant under his name, because Max Planck explained the black body radiation in 1900. Okay, because he wanted to explain the experiment of black body radiation. So last day I actually started by knowing what is the radiation. Radiation means wave. Wave means disturbance, fluctuation. Wave may be sound wave, like the vibration of the matter. Suppose I'm clapping, so I'm creating sound wave. Wave may be vibration of the electric field. Okay, maybe vibration of the magnetic field. So they're electric and magnetic wave. And maybe vibration of electric and magnetic field mutually perpendicular to each other and moving. That makes an electromagnetic wave. Okay. So the or light wave is an electromagnetic wave. Only point is that its wavelength is very specific, 4,000 to 8,000 angstrom. Below 4,000 is infrared. Above, ultraviolet light. Above 8,000 is infrared light. So there are it's a huge family actually. Our visible light is only a small member of it. Okay, above very large small wavelength radiations like X-ray, gamma ray. Very high wavelength radiations like heat waves, radio wave, frequency wave. Just below the visible light, you can see. So all these are called electromagnetic waves. Now experiment, the concept of electromagnetic wave is needed because the definition of black body, is all related to whether a body absorbs electromagnetic radiation or emits electromagnetic radiation. At low temperature, I told you a body can be black because of those red lines. If it can absorb any radiation fully, incident of any radiation completely, and, and that means its ability of absorption should be 100%, and no selection rule, or any color will be fully absorbed. Color means any wavelength fully absorbed, and if you hit it, it will emit radiation of all possible wavelengths. Okay, so ideally a black body should have 100% ability of absorption, 100% ability of emission. But I told you ideal, the word ideal is used for something which is not real, not practical. So this is how a black body in practice can be obtained. It is, I told you, this is a like a cavity, hollow cavity, like a chamber on a three-dimensional box. It's an empty box. All the walls of the box are coated with lamp black to get you very good absorption, because it has got huge absorption ability, 95 to 98%. So whenever a radiation comes in, so say with intensity I1, it is incident on a black surface, 98% of it is absorbed. If the reflected intensity is I2, it is 2% of I1. Okay, if the reflected intensity is incident on another black surface, if the reflected intensity is I3, it is 2% of I2, much lesser than I1. So from I3, it goes to another black surface. So 98% of I3 goes up, absorbed, and it becomes say I4. I4 is 2% of I3. So again, radiation of intensity I4 is another black surface. So if it is I5, so you can say after incidence it gets reflected further. So if the reflected intensity is I6, okay, so it is again 2% of I5, and it's a cumulative process. It will go on and on and on and on, and each incidence means huge absorption. As a result of that, almost entire radiation and gets enclosed inside the cavity, and we get huge absorption ability. Okay, but there will be some practical losses as shown by the red arrow. So you can never get 100% absorption ability. 99.9% you can achieve. There will be another loss also if normal incidence is there. If a radiation comes, hits perpendicularly to the surface, so there will be 2% loss, because 98% will be absorbed. Now to minimize that loss, some diffusers or pointers are used. Okay, so all these things you learned in schools possibly also. Okay, in school days you learned it. Now this body is black because of absorption ability at a low temperature. So what I did the other day, I hit, so this is the animation. Okay, if you hit it, it emit radiation, but I can call it black if it emits all types of radiation. Now then comes the question of hitting. I told you if you hit it, and I can call it a black body if it emits all types of radiation possible. Okay, all the radiations you can imagine. If everybody comes out, then I can call it a black body. Okay, then experiment was done. Whatever with the radiation coming out, it was passed through phosphorus prism, so it was dispersed. For every component wave, corresponding intensity was measured and was a graph like this was obtained. Now this graph was now plotted in a graph. Sorry, a table was obtained rather. For each wavelength emitted, lambda 1, lambda 2, lambda 3, practically very small to very large lambda. For every lambda, energy was measured and plotted. Okay, if you plot it, it looks like this much. It's a very interesting graph, and it's not a known graph to us. Okay, initially increases, finally decreases in between passing through maxima, and if I hit it further, I will get similar graphs again, but at a high with a high temperature, the lab maximum gets shifted towards the origin, and ultimately we end up with the Wick's displacement law that you know from the previous discussion. So now what shall I do actually? I will now concentrate on one of the graphs. Okay. Suppose the graph that I obtained by hitting the black body from temperature T1 to a temperature say T2. So what happens? Suppose T1 is 1000 degree Kelvin. Suppose initially the black body was at a temperature T1 is equal to uh, 300. Now it has moved to 1000 degree Kelvin. So now suppose I give you this graph to you and I ask you what is the total energy. I ask you this question in the last at the end of the previous video lecture. What is the total energy emitted due to the heating of the black body because radiations are going out of the box. Okay, what is the total energy emitted out of the box? Now the answer this question I ask you, we will be taking a different route actually. You look at the graph. Okay, suppose from the box only three wavelengths are emitted: lambda 1, lambda 2, and lambda 3. So question is that what is the total energy emitted because of the three lambdas, lambda 1, lambda 2, lambda 3. So from the graph, I can get the corresponding energy, say E1, E2, E3. So total energy emitted because of the emission of if only three lambdas were out, E1 plus E2 plus E3. Okay. Suppose four wavelengths are out of the box. So I have heated the black body, only four lambdas are out, lambda 1, lambda 2, lambda 3, lambda 4. So if I have to get the total energy emitted out of the box due to the emission of four lambdas, it will be E1 plus E2 plus E3 plus E4 because they are the energy corresponding to the four lambdas. So that means if I have to calculate the total energy emitted by the black body, it will be the summation of the corresponding energies. If four wavelengths are emitted, E1 plus E2 plus E3 plus E4. If it is three wavelengths emitted, it is E1 plus E2 plus E3 like that. Now the question is that if it is a black body, theoretically it is emitting all types of wavelengths from 0 to infinity. Practically it's very small to very large. So basically, if I wish to know what is the total energy emitted due to all the lambdas, so basically this sum is going to be a very huge sum. Okay, it will be an infinite sum because everybody on the lambda axis is contributing because for every wavelength, all wavelengths are out of the box. And according to the graph, you can see it's a continuous graph. So for each lambda, I will get a contribution. So the total energy emitted by the black body for all lambdas will be a huge sum. E1 plus E2 plus E3 plus E4, and so up to infinity. So this becoming a very long sum, huge sum. But there is a glimmer of hope. Hope is that if you look at the graph, it's a continuous graph. And you know, so what you are doing, if you add those E1, E2, E3, E4, E5, so what you are basically doing this much. Okay, look here. If you add all those things, okay, so for lambda 1, so for lambda 1, say, your energy may be E1. E1. For lambda 2, your energy, so this is your E1. For lambda 2, your energy may be E2. So you're adding this energy, C1, E2. For lambda 3, suppose your energy may be E3. So you're adding them. For lambda 4, your energy may be E4. For lambda 5, your energy may be like E5. So suppose this is lambda 5. So if that this suppose similarly for each lambda, that means you are getting e's. Now how many e's you get? Point is that all values of lambdas are right because all wavelengths are out. So for each of lambda, I am getting a point on the graph. For each lambda, I am getting a point on the graph. So for every lambda, I am getting a point. So each point means one of the e's. So if you are doing all you are doing this sum, that means you are actually adding all points, all the e's, all points on this continuous path. You see, you are adding all points on this continuous path because all wavelengths are out of the box. Okay, all points on this continuous path, you are actually adding all the points. Okay. So and summation over a continuous path is called an integration. So total energy emitted is therefore an integral like this. Okay, this integration. Okay, from 0 to infinity. And E lambda is the functional formula of the energy emitted. Now the question is that so my next job is to do this integral and calculate the total energy emitted out of the black body. But there is a problem. Problem is that I can only perform this integral if I know the value of E lambda. Now the question is that E lambda is not a known graph to me because this is what is E lambda? E lambda is the equation of this graph. Question is that this graph is not a short straight line so that I can write down m lambda plus c, okay, and do the integration. It is not a parabola so that I can write down the equation of a parabola and do the integration. It's not a circle. It's not an exponentially growing or decreasing graph. It is actually a mixture. Sometimes grows, sometimes falls. So point is that this graph is not falling into our known graphs. Because it is not falling into the known graph means that equation you know. You do not know the equation of the graph. So if you do not know the formula of the graph, you cannot calculate, do that integration. And if you can't do that integration, that means you cannot calculate total energy emitted out of the black body, and your experiment with black body radiation remains incomplete. Your job was simple. You have heated a black body, and you wish to know what is the total energy emitted by the black body. And that you can do if you do that integral. But because you already have the experimental graph, point is that you can only do it if you know E lambda. If you don't know E lambda, you can't do it. And which you do not know, that is the problem. Okay. And two options are there. That is quit today, that syllabus is complete. I do not know how to get E lambda, so you can't do anything. Our experiment with black body radiation is incomplete. Or you do something. So obviously we'll take a positive path. That means we'll try to explore that how do I get E lambda. Our problem is that I don't know the formula of the graph. The same problem was faced by scientists 120 years back also. So what they tried to do, they tried to get a correct formula of E lambda. So what is your problem? Your problem is to get a formula of that graph. So what scientists tried to do, they came up with various propositions. Okay, and the first person to come forward in this regard was Wien himself. Okay, Wien himself was the first person to propose something. So what Wien did, so your problem is that you do not know the formula of E lambda. So what Wien is trying to do, he is trying to give a formula of this E lambda. Now that formula, that proposal of Wien, is popularly called Wien's law of black body radiation. Don't get confused with the displacement law. Displacement law talks about how the maxima will shift because of the rise in temperature. But Wien's law is there to give a formula of E lambda because problem is very severe. I can't do a simple integration because I don't know the formula of the graph. So that is what they are trying to do. Now this is the deduction of Wien's law. All these things are not in your course. So basically this is the formula of E lambda as was given by Wien. Okay, this is the formula of E lambda as was given by Wien. So this full deduction is not there. So just get it. It is energy emitted that for a given lambda or energy density, whatever you say. Some constant a by lambda to the power 5 exponential minus b by lambda kt, where k is a Boltzmann constant, t is the absolute temperature. So this is a formula of B lambda as is given by Wien. So what is your problem? You want to know formula of B lambda. You've got it. So what is your next job? Your next job is to do the integration shown here. But will you do the integral? Wait a bit. You can only do the integral if this formula is a right formula, correct formula. So you have to judge it. You should like to learn it. Cannot accept anything arbitrarily. You have to judge the quality of it, applicability of it. So your job is to judge it, whether it is right or wrong. So how do I judge it? That is the question. We can judge it. That means if this new formula of B lambda, it can reproduce the experimental graph. Question is that can it reproduce the experimental graph? And not only reproduce, it has to reproduce a full experimental graph from 0 to lambda infinity. So that is something you have to do now. You have to judge the correctness of this formula. So what shall we do now? It's very simple. Okay. You see, we can explain that e to the power series in that way. Okay, like 1 by b lambda 1 minus b by lambda kt plus b by lambda kt square by 2 factorial minus b by lambda kt to the power cube factorial plus b by lambda kt to the power 4 factorial and so on. Okay, we can do that. So if you do so, one thing you notice, you see, please try to apply common sense. Lambda 5 is in the denominator. So when you multiply by lambda 5 inside, first term pi is a by lambda to the power 5. Next term will be b by ab by lambda to the power 6 and the on kt kind of thing. Next term will be a b square lambda to the power 7. So power of next term will be lambda to the power 8. Next will be lambda to the power 9. So power of lambda is continuously growing up in the denominator. So relationship of E with lambda is proportional to 1 by lambda to the power n, where minimum value of n is 5. That is the first term. So n will be, so lambda, it will be like 1 by lambda to the power n. So n will be 5 or more. So what does it tell? If I increase lambda by 10 units, it talks about a fall in energy by 10 to the power 5. Okay, or more. So what does it imply? It implies a quick fall if there is a, like this. If it implies that if this is my dependent graph, if this is my graph, suppose lambda is, this is the lambda axis and this is the a lambda axis. This tells us suppose for a small change in lambda, there is a quick fall in a lambda. So slope of the graph should be very high. And you see, it is only true over this portion of the graph where there is a quick fall in the graph is noticed. So this is where this Wien's law is applicable. Problem is that lambda is in the denominator. So it always tell, if I increase lambda, E lambda should always fall. Okay. It is telling me if I increase lambda, E lambda should always decrease. Okay. So if you write lambda, E lambda should always fall because it is in the denominator. So that's why it is never applicable to this portion of the graph, where you can see that lambda, E lambda goes up because of the rise in lambda. Question is that will you accept it? Never. You should not accept it. I can only accept a graph formula which will reproduce a full graph. It is only partially true what the portion shown by the arrowhead. So it is not explainable for it can't explain the region at all, or the region below lambda maxima, because there is opposing nature. This expression only talks about fall in lambda with the growth in lambda. Okay, and which is true a bit, essence only partially, because it talks about a very quick fall as I've shown in the picture there. It is only partially true about the arrowhead shown by the graph. So obviously, unless and until it is explaining the full graph, we are not in a position to accept it. So tata bye bye. So now what you have to do, Win is incorrect. So now two more person will come into business. They are Raleigh and James. Now what Raleigh and James did before proposing a new expression of E lambda, they actually scrutinized the way Win has done it. So they actually try to answer. You see, I ask you a question. Suppose I've got three graphs. This is the first graph, this is the second graph, this is the third graph. Three graphs are there. And I ask you to write down the equation of the first graph. All of you, we should write down this is the equation of the first graph, or is equation of a straight line. And this equation of the second graph is very similar. It is also a straight line, but the slope is negative. So you may write down minus mx plus c, but you can't do it. And the next, this is the equation of parabola, the third graph. So that means if I give you some graph, you can write down the equation of the graph if you know the formula. Now, question is that to write down the first case, y is equal to mx plus c, do you need any physics knowledge? Never. Just by knowing the basic coordinate geometry, you can write down. So that means what I'm trying to tell you, when you try to write down the equation of a graph, your approach may be purely mathematical. Just to fit the graph, you write down the equation. There is a mathematical, okay. That may be one of your approach. Or, okay, you may try to, because our experiment with blackboard radiation is a physics experiment. So even if you try to put a equation of the graph, you have to put some physics behind your background. Now, Rayleigh engines actually examine the approach of when it has a thermodynamical view, thermodynamical basis. Otherwise, it lacked proper physical significance behind the expression of E lambda. So what Rayleigh did, that they have tried to come out of this mathematical block, I should say, because her approach is that you get a graph just from your basic memory or your common sense, you write down the equation of the graph, just like the way I've done it. But the idea is that you can't do that when you are explaining a physics result. Whatever you do, whatever you write down, there should be physics background for that. So what Rayleigh engines did, they tried to put a lot of physics, lot of physical meaning behind their expression of what lambda. So what they did is they made some assumption. Assumption one is very simple. This cavity is full of radiation of all possible wavelength at a temperature T1. So when you hit them, those radiations will go out of the box. Second assumption is that, okay, second assumption, before I tell you second assumption, I've got a point to tell you. If you look at the experimental graph of the black body radiation, if you look at the experiment of black body radiation, okay, initially, this graph, initially I've got a black body at a temperature T1, I've heated it to a temperature T2, and suppose I get this graph at 1250 degree Kelvin. I hit it more, suppose to 750, you get the second graph. I hit it further, I get the third graph. The question is that, okay, fine, I'm hitting, I'm getting a lot of more energy, all these things are happening. Okay, but the question is that, you see, how do you grade these graphs? You're hitting a black body, radiations are out of the box. Now, assumption one tells us that this cavity is full of radiation. So when you hit them, they are getting out of the box. So after all radiations are gone out, it is supposed to be an empty box, but it is almost like a magic. So again at a high temperature, say T3, again all the radiations are out of the box. Question is who is supplying it? Again, it's almost like the water of India magic of PC Sarkar, Junior, that again you hit it, okay? Again at temperature T4, again all radiations are out of the box. So that means there will be somebody inside who is playing some role, okay? There must be somebody who is helping it, who is providing radiation of all possible wavelengths inside the cavity, so that it is always packed with radiation. That is the assumption one of Rayleigh engines. So they actually try to explain who is providing the radiation. The answer is encoded in the idea of Rayleigh engines. Rayleigh engines thought, okay, fine, this cavity is full of radiation, but who is supplying it? Answer is that atomic oscillators. You see, any cavity is full of made of atoms. You can see these white balls are the atoms, periodic arrangement of the atoms. So how they are arranged? Okay, none of them are static. All of them are vibrating. They are attached to some type of spring, as if they're all of them are vibrating. None of the atoms are static. About the mean position, okay, they are vibrating as you can see there. Okay, about the mean position they vibrate. Okay, as if they are connected by some balls, they are connected by some springs, and they vibrate along these arrowheads shown there. Okay. So every atomic oscillator is vibrating. So Rayleigh engines thought this vibration is harmonic vibration. So everybody vibrates with this fixed harmonic vibration means oscillation with fixed frequency. So I've got infinite atoms. So all of them are oscillating. Okay. So they can vibrate or oscillate with infinite possible frequency. Okay, and so the atomic oscillators are there. Now you see, okay, if you find their oscillators, I want to take your attention to a word called charged atomic oscillator. You see, I've written there charged atomic oscillator. Where from the word charged come into business? The word charge is coming into business. Okay. These are all atomic oscillators which are making the walls of the cavity. Embroidery is vibrating. Okay. The suppose all the atomic oscillators are vibrating. Okay. Suppose the first one is vibrating with the frequency. The first one is vibrating with the frequency is a new one. New one may be anything between 0 to infinity. The second one is vibrating with maybe some frequencies in U2. This is vibrating with some frequencies in U3. So all the atomic oscillators are vibrating with its own frequency. Of infinite atomic oscillator, they can vibrate with infinite possible frequencies. Okay, and they are all charged oscillator. You know, if we consider an atom, any atom has got two parts. One is a nuclear part, and another is a charged part. Now it is thought that nucleus is too heavy to move; it does not move. So atomic oscillation means basically oscillation of the electronic part of the oscillation. Okay. So every atom is oscillating, every atom is vibrating, but all of them are vibrating with their own frequency. And every atom is like a charged oscillator. Why? Because every atom has got a two part, nuclear part which is static, and this electronic part is the electron mass is much lesser compared to the entire atomic mass. So atomic vibration means not the static part, but this charged part is vibrating. This charged part is vibrating. And according to electrodynamics, if any this is a vibration or oscillation of a charge. And according to electrodynamics, if anybody is under oscillation, say pendulum, if it is oscillating, it should be accelerated. Okay, it should have some acceleration. And oscillate. So these electrons, they are actually oscillating. Okay, if a charge do oscillate, they are, according to electrodynamics, they will emit radiation. So all these atomic oscillators will add radiation to the cavity. All of them will be adding radiation to the cavity because all of them are vibrating, are attached with some springs, as you can see, and every atomic oscillator is vibrating with its own frequency. This is vibrating with this frequency, a new one. This is vibrating with frequencies a new two. New one is anything between 0 to infinity. This is vibrating with maybe frequency new 3, and so on. Infinite atoms vibrating with infinite possible frequency. Okay, so all of them are vibrating, and if they are like atomic vibration means vibration of the charge part. Okay, and if a charge oscillates, that will be emitting radiation, and that radiation will be added into the cavity. So that radiation is added with the cavity. This cavity is full of radiation. So who is supplying the radiation inside the cavity? The atomic oscillators. Okay. Now the question is that if they are, so that means this process is always on. The atomic oscillators are okay. They are vibrating about the mean position. They are basically charged oscillator. So they will emit radiation, and that will be added to the cavity. Okay, this will be all added to the cavity. So ultimately, this is always full of radiation. Now, if you heat the black body, what would happen? Okay, the thermal energy of this energy of the atomic oscillator, okay, goes up. Understand? So what would happen? So the some of the atomic oscillators also take up energy because if you heat it, they will take up energy from the cavity. And in general, because all of them are oscillating, so all of them are vibrating with their own frequency, nu1, nu2, nu3, etc. Okay, so all of them, these are all charged oscillator, so they will be adding radiation to the cavity. But not only adding radiation to the cavity, some of the atoms might take also because they are getting excited because of hitting it. So it's a dynamic process. So that this cavity is always full of radiation. And according to religions, this is happening continuously. So that this everything, every time it is jam packed. So the assumption one is that cavity is full of radiation. Second assumption two is the explanation of who is providing the radiation. Answer is that atoms making the walls of the cavity. They are all oscillating, they are charged oscillator. If a charged oscillator, it emits radiation and that will be added to the cavity. Okay, that will be added to the cavity. So it is full of radiation every time it is getting radiated. Okay, like this. Understand? So what Rayleigh engines did, based on this idea, the atoms are vibrating, they are oscillators, losing energy, taking energy, all these things. So what they did ultimately, they also have to come up with a new expression about E lambda. Now this is a new expression of E lambda that you can see in the screen, 8 pi kt by lambda to the power 4. Okay, this is the expression, new expression. In this expression, 8 is a constant, pi is a constant, k is constant, t is constant for a given black body. It all depends on lambda. And you see, our next job is obviously to test whether it is right or wrong. So how do you do so? Okay, you choose few regions. You see, first you consider this region is a region where lambda is very, very high. What do you notice? If you increase lambda, actually, you can see if you increase lambda drops down, and that is happening here. Okay, so over this portion of the characteristic graph, okay, it is okay because it is in the denominator, numerator is all constant. So if I increase lambda should decrease. So it's okay here. But the problem begins here over this region. As lambda, this portion, as lambda is trying to approach zero, then what is happening? As lambda is trying to approach zero, if you look at the formula in this expression, denominator is going to be zero and it becomes a limiting problem. Now, if you put the limit lambda tends to zero, okay, how does it happen? If you put the limit, say limit lambda goes to zero, so if you put the value of lambda equal to 0, is 8 pi kt by 0. So ultimately it goes to infinity. So the idea is that you see this law is very good for high lambda, but problem is happening at very low lambda over this portion of the if you look at the, if I mark it, say this portion of the graph, you see what does it show? This graph is okay here. But the moment of you are actually crossing maxima, it is also going up. Okay. The moment you are crossing maxima, this is graph shoots up because it is talking about it is going to infinity as lambda goes to 0. But you see in the experiment there is an opposing nature. Experimentally, as lambda to the left of maxima, lambda is going towards 0, not infinity, what Rayleigh engines are telling. So you can see that Rayleigh's prediction is taking that lambda will go to almost infinity. Sorry, E lambda will go to infinity as lambda goes to 0. Okay. This problem that you are facing here, the theory is telling that it should go to infinity. Theory means theory of religions, and experiment tells us no, it should begin at 0. Okay, now this problem has got a name. In literature, this is called ultraviolet catastrophe because ultraviolet range is the small wavelength range. So in this region, you can see that there's a Himalayan blunder because theory tells, this is the theory is telling, theory of religions is telling that it is going to infinity. And the experimental religions are telling, this is the experimental graph of the religions. Uh, experimental graph. Okay, you can see here. So what you notice here, there is a huge contradiction between the theory and experiment, and you can see there to it's a Himalayan blunder that is committed by Raleigh and by Raleigh's proposal. This is called ultraviolet catastrophe. So question is that will you accept it? Answer, never. It is only partially true and it is producing pathetic results as lambda goes to zero, which is called ultraviolet catastrophe. So obviously, even if you have heated the body from T1 to T2, you see there, I have drawn it here on the screen. As lambda goes to zero, as for high value of lambda, it is good enough. Okay, theory and experiments are agreeing with each other. But the moment you grow to lambda, very lambda, you see lambda, say small values of lambda, experimentally it is going up, but in the expression lambda is in the denominator, it will always tell the opposite story. And this is the most poorest result. Okay, that as lambda goes to zero, you can see there E lambda also goes to infinity. It's a huge blunder. That is the curve of ultraviolet catastrophe. Experiment tells it goes to zero. Theory is telling it will go to infinity. This is called ultraviolet catastrophe. So it permits us that again correction needed. Now the correction was made by Max Planck. So how Planck made it? Okay. So let me tell you. Okay, wonderful video is here. Please experience it. So who is doing the wonder? Radiation. So again, what Planck did, he made few assumptions, and be careful about the third assumption of Planck, something new. That is the birth of quantum ideas. Okay, so wait for that. Our journey with quantum mechanics 1 will continue. Okay, so please be patient. Okay, so we'll just start discussing about our journey quantum mechanics 1. Now I give a home task again to you, is that you just try to know about photons a bit. Okay, you studied photons in your uh, you studied about photons in your modern physics courses in 12th standard classes. What photon is? Photon is a piece of energy. What is the energy of a photon? H nu. H nu is called quantum of energy. This term will come next day. Okay, when I will be talking about Planck's idea. Okay. And that where you learned that in photoelectric effect. That was an experiment of 1905. But Planck, when he is doing it, he is doing it in 1900. So 5 years before, Planck has got some beautiful things. So that will come to the next.